Welcome students for the third lecture of physical chemistry. We are going to see for today's lecture regarding the Heisenbergs Uncertainty Principle. For last lecture, you learned the de Broglie equation and it explains the dual nature of matter as a particle as well as wave. Similarly, the electromagnetic radiation or energy, it also behaves as a particle and a wave. Then the another scientist, Heisenberg, he stated his principle and it is known as Heisenberg's Uncertainty Principle. All of you know that the classical mechanics it explains the nature of big matter or big particles, and according to classical mechanics, simultaneous determination of momentum and position, it is we can determine accurately and precisely at the same time. This is the classical mechanics. With the help of classical mechanics, we can simultaneously and accurately determine the position and momentum. But the quantum mechanics, it does not allow this. Suppose, for example, our moving body or moving particle, it is electron and it has a very less dimensions or micro size, and according to the Heisenberg's uncertainty principle, the simultaneous and accurate determination of position and momentum of electron, it is impossible. His hypothesis, in his words, he stated as one cannot simultaneously determine both position and momentum of an electron because due to the dual nature of electron, it behaves as a wave as well as a particle. And to overcome this difficulty, Heisenberg gave his equation, and the equation is like this. Here I repeat once again. According to classical mechanics, simultaneous and accurate determination of both position and momentum of moving body at any point cannot be possible, but for microscopic particles such as electrons, it is not possible to detect its position and velocity or momentum accurately and simultaneously at any point because it exhibits dual nature of wave and particle. So, mathematically, Heisenberg's equation or principle, it is stated as delta x into delta p, it is greater than or equal to h cross, where delta x is the uncertainty in position, in the determination of position, and delta p is the uncertainty in determination of momentum, and h cross, it is equal to h by 2 pi, where h, it is the Planck's constant. And it is explained like this. Here, both the position and momentum of particle such as electron at any time cannot be determined accurately. If we determine position, that is location, very precisely, then the velocity or momentum cannot be determined accurately. There is uncertainty in the determination of position and momentum of an electron simultaneously. The uncertainty is a function, the uncertainty is a fundamental limit of nature, and it is for all conjugate quantities such as position and momentum, energy and time, etc. The Heisenbergs have given mathematical equation for the sake of explanation of this statement. This is the explanation of this statement in the form of mathematical equation. Again, I will repeat this. Delta x into delta p, it is greater than or equal to h cross, where delta x, it is equal to uncertainty in position, delta p, it is equal to uncertainty in momentum, and h cross, it is equal to h by 2 pi. Again, h, it is equal to Planck's constant. And this is the, if delta x is low, that means in the determination of position, if we have uncertainty low, then the uncertainty in the determination of position, it is maximum, and vice versa. It is shown in this diagram. Again, this uncertainty principle, this is the principle of quantum mechanics, and the position and momentum of particle cannot be accurately measured at the same time. Suppose we have m is the mass of this particle and v is the velocity along this direction of this particle. Then m into v, it is the momentum of this particle, and here the Heisenberg's principle, it is also mathematically explained as delta x into delta p, it is greater than or equal to h by 4 pi, where h, again, it is equal to Planck's constant. Hence, the Heisenberg principle can also be stated as the product of uncertainty in position delta x and uncertainty in momentum, that is delta p, along x direction, is always greater than or equal to Planck's constant h. If we measure the position of microparticle such as electron precisely, that is, if delta x is small, then uncertainty in momentum delta px is increased. Here I have shown this. If delta x means position, uncertainty in position, if it is less, then delta p is maximum, and vice versa. I will repeat this once again. If more precisely we can determine position, then less accurate is the determination of momentum. So, if position of electron is determined accurately, then we can speak of a probable value of momentum of the electron and vice versa. We can speak about the probable position or probable momentum of the electron in the orbit. And for your syllabus, this Heisenbergs Uncertainty Principle, it is the it is about it only. That means, according to Heisenberg's uncertainty principle, it is impossible to determine simultaneously and accurately the position and momentum of microparticle at a time. This is the statement of Heisenberg's principle, and in such a way Heisenberg uncertainty principle introduced the probability approach, that is, we can find the area in a space where probability of finding the electron is more instead of exact location. And this is about the second point, Heisenberg's uncertainty principle. Then we turn towards the concept of energy operator. And for your study, there is a Hamiltonian operator. Hamiltonian operator, it is a total energy operator. Here, the quantum mechanics, it is based on the mathematics, or mathematical basis of quantum mechanics requires the concept of operators. Then, any mathematical operation such as differentiation, integration, addition, subtraction, multiplication, division, square root, etc. can be specified by certain symbol known as operator. In short, the operator, it is nothing but any mathematical operation which is done on the other function. Here, operator is an instruction to carry out certain operation. It is a symbol or a rule for the transformation of a given mathematical function into another function, and you are you know what is the differentiation, what is the integration, what is the addition, what is subtraction, multiplication, division, square root. These are the mathematical operators. Then it has no physical meaning if it is only written. That means if we write only any operator symbol, then it has no any meaning. For example, suppose we have drawn a square root sign, and this is one operator, and if any quantity or any number is not put under it, then it is a meaningless. That operation is a meaningless. If we put any number under the square root, then it transforms the given quantity into its square root. Then the another operator is differentiation operator, and we denote that differentiation as d by dx, which transforms the function, for example, x raised to n, to another function as a n x raised to n minus 1, or a function sin x to the cos x, etc. Generally, operator is written with a symbol and that cap over that overhead. An operator is written like a overhead, and you are familiar with the certain operators as linear operator, conjugate operator. Then f of x and g of x are the functions of a operator and c is a constant. Then we can have the addition or subtraction of the operators acting on the function. In general, any physical quantity in classical mechanics like kinetic energy, potential energy, momentum of a molecule, etc., can be represented in quantum mechanics by mathematical operations. Then, the Hamiltonian operator. Here, I will explain you in a detail what is the Hamiltonian operator. Here, the Hamiltonian operator corresponds to total energy of the system, and this operator is called as Hamiltonian operator. It is represented as here the sign of Hamiltonian operator. It is a capital H. On its head there is a gap and it is written like this, Hamiltonian operator. This is the Hamiltonian operator representation. And in the form of equation, we can write the total energy of the system H, that means total energy, it is equal to the sum of kinetic energy, it is represented by letter T, and potential energy, it is represented by phi. In the classical mechanics, the Hamiltonian or total energy of a system expressed by the Hamiltonian. Then the Hamiltonian is a sum of kinetic energies of all the particles plus the potential energy of particles associated with the system, and it has different forms. This operator, it has different forms. We will see one form of the Hamiltonian operator. Then the Hamiltonian operator in the form of operator, it is written as here already you know, by putting cap over the Hamiltonian, that means energy operator H, we read this as a Hamiltonian operator and it is equal to the kinetic energy operator plus potential energy operator, where T it is the kinetic energy and phi it is the potential energy. Then the equivalent equation for the energy can be given as here Hamiltonian operator into psi, it is equal to E into psi, where this psi it is a probability function. Now, according to classical mechanics, total energy is sum of kinetic energy and potential energy. You know that kinetic energy it is equal to 1/2 mv square, and in the form of momentum the kinetic energy it is expressed as 1 into p square by 2m, where p means momentum it is equal to m into v, where m it is the mass and v it is the velocity. Here we have expressed the kinetic energy in the form of momentum and it is equal to p square by 2m. and the potential energy, it is equal to phi, as a potential energy is a function along the three coordinate axis. So we write phi, it is equal to phi in a bracket x comma y comma z, that means along three coordinate axis, and the Hamiltonian energy we can write as a 1 by 2m in bracket px square plus py square plus pz square plus phi in bracket x comma y comma z. That means we have written the moment kinetic energy in terms of momentum along x coordinate, along y coordinate, along z coordinate, because already we have the equation for kinetic energy in terms of momentum as 1 half mv square, it is equal to p square by 2m. Therefore, we have taken here 1 by 2m, and the p into x square plus p into y square plus p into z square, these are the momentum along x coordinate, y coordinate and z coordinate, and this is the potential energy along three coordinates. Then the corresponding Hamiltonian operator we can write as putting a cap over this h, and it is equal to 1 by 2m in bracket momentum operator into x square plus momentum operator along y axis plus momentum operator along z axis plus the potential energy operator along xyz. Here the potential energy, as it depends on coordinates x, y, z. So the potential energy operator we can write like this. Then putting these values in Hamiltonian operator, we get here Hamiltonian operator, it is equal to h square upon 8 pi square 8 m pi square in a bracket dou square by dou x square plus dou square by dou y square plus dou square by dou z square plus the potential energy operator along x, y, z. Then this Hamiltonian operator we can simplify like this. It is equal to minus h square upon 8 pi square m into del square plus potential energy operator along x, y, z, and here del square, it is equal to dou square by dou x square plus dou square by dou y square plus dou square by dou z square, and it is called as Laplacian operator. Then comparing this equation with the energy equation, we can write Hamiltonian operator into psi, it is equal to minus h square upon 8 pi square m in a bracket dou square by dou x square plus dou square by dou z square dou y square plus dou square by dou z square into psi plus potential energy operator along xyz into psi, and it is equal to E psi, and this is the general form of Schrödinger equation for stationary state. Here I have explained you the Hamiltonian operator. Though there is a mathematical part, you will understand it is quite easy if you have attention in the understanding, then you will get the idea regarding the energy operator. Once again, I will explain you the energy operator, and for your study there is a Hamiltonian operator. Here the operator corresponding to total energy of a system is called the Hamiltonian operator, and it is represented by putting a cap over H, and it is read as Hamiltonian operator. Then all of you know the total energy of a class energy of system in a classical mechanics, it is represented by H, and it is the sum of kinetic energy and potential energy. Kinetic energy represented by capital T and potential energy represented by capital V. That is total energy of the system H, it is equal to T plus V. Then the corresponding Hamiltonian operator, it is written as like this, a cap over H, it is equal to Hamiltonian operator, and cap over T, it is the kinetic energy operator, and a cap over V, it is the potential energy operator. The equivalent equation for the energy, it can be written as H operator, that means Hamiltonian operator into psi, it is equal to E into psi, where psi it is a probability function. Then according to classical mechanics, the total energy is the sum of kinetic energy and potential energy. I have explained this well. You will understand better. Kinetic energy, it is equal to 1 half mv square. In terms of momentum, it is written as p square by 2m. And potential energy, it depends on coordinates. Therefore, we can write like this: v in a bracket x comma y comma z. Then the total energy in terms of momentum, we can write 1 by 2m in a bracket px square plus py square plus pz square plus potential energy along 3 coordinate axis, and the corresponding Hamiltonian operator we can write like this. Here the Hamiltonian operator, it is equal to 1 by 2m, then momentum operator along x axis, y axis, z axis plus potential energy operator. Then the momentum operator is given as h upon 2 pi I into dou by dou x. Here the momentum operator along y-axis, it is given as h upon 2 pi I into dou by dou y, and momentum operator along z-axis, it is given as h upon 2 pi I into dou by dou z, and the square of this, that means the momentum operator along x-axis, we can write operator p into x square, it is equal to the multiplication of h upon 2 pi I into dou by dou x into h upon 2 pi I into dou by dou x, and it is equal to minus h square into dou square upon 4 pi square into dou x square. Similarly, along y-axis, here we have minus h square upon 4 pi square into dou square by dou y square, and along the z-axis we can write h minus h square upon 4 pi square into dou square by dou z square. And this minus sign, it is because of this I into I, it is the I square, and it is equal to minus 1, because I, it is equal to square root of minus 1. So we have this negative sign. Then putting these values in the Hamiltonian operator, we get this equation. Hamiltonian operator, it is equal to h minus h square upon 8 pi square m into dou square by dou x square plus dou square by dou z square plus dou square by dou z square plus potential energy operator along 3 coordinate axis. That is, we replace this by Laplacian operator, and we have the equation as Hamiltonian operator, it is equal to minus h square upon 8 pi square m into del square plus the potential energy operator along x comma y comma z. As already I have told you, del square, it is called as Laplacian operator, and it is nothing but dou square by dou x square plus dou square by dou y square plus dou square by dou z square. And by putting this value, we can have the Hamiltonian operator as Hamiltonian operator into psi, it is equal to minus h square upon 8 pi square m in a bracket del square psi plus potential energy operator into psi. And this is the general equation which is derived by means of Schrödinger for stationary stage. I mean, you can understand it. If there are any doubts regarding the understanding, then you will ask your questions to me. Then I will try to answer your questions. So thank you very much. And for today's lecture, we are going to see the derivation of Schrödinger wave equation. Best of luck. Study well. Thank you.